In our last video, we talked about the complex refractive index and how it relates to the dielectric function and where that comes from in terms of the interactions of electrically charged components within atoms and molecules and solids. This time we're going to talk about, now that we've derived the complex refractive index, what the effect is on light. What effect does the complex refractive index have on light? Let's start by considering our light as an idealized sinusoidal wave. We can write our incident radiation as A equal to A0 e to the minus I times omega t minus zeta x. This is just a wave equation. And the A0 is the amplitude of the wave, the omega is the angular frequency, and the zeta is the wave number, also known as 2 pi over lambda, the wavelength. Usually we would denote this wave number by k, but because, as described in some of our previous videos, the letter k is overused and it will be used again in the complex refractive index, so we don't want to use it here. We've got this plane wave, this simple wave. As the light enters a medium, the velocity of light is affected by the medium, and so the speed changes by the refractive index. So we've got the speed v is given by the speed of light in vacuum divided by the complex refractive index. So if we put that into our wave equation, we now have A equals A0 times e to the minus I omega t minus zeta mx, where m here is our complex refractive index. And now what I'm going to do is to put in the complex refractive index in terms of the real part n and the imaginary part k. And now I'm going to multiply this thing out. And so what I get is an equation for the light that is inside the medium is given by A0 e to the minus I omega minus zeta nx, all times e to the minus zeta kx. You'll see that we've got something that looks like a wave equation here and something that has a real exponent here. We're going to want to extract some optical constants based on this interaction. So remember that what we're looking at in terms of what we see in the lab is we're measuring the flux after the light has passed through some material, and it depends on what the intensity of the light was before it entered the material, the absorption coefficient of the material, which is wavelength dependent, and the thickness of the slab material. And this is known as Beer's law. Now, if we compare that to our wave equation that we've been using, now we've got the wave is A0 e to the minus I omega t minus zeta nx e to the minus zeta kx. And we can see here that the first part, the A0 part, is the wave, and how it is affected as it goes through the medium is this last exponent that is real, that is this kappa abs x. Now remember that the intensity of the light wave is proportional to the amplitude squared. It's not just the amplitude. Well, we need to square this. We put in an extra 2 in our equation here. And so what we find is that this e to the minus zeta kx becomes e to the minus 2 zeta kx, and that's equal to this e to the minus kappa abs x. And so what we have is kappa abs is equal to 4 pi over lambda times k. So remember, we've got this zeta k, which we then multiply by 2 to get the squaring. And then the zeta is just 2 pi over lambda. So that gives the 4 pi k over lambda. And so this is how we get to this. The important thing here is that we can measure how the light is missing, how much light is missing once it's passed through material. And if we can measure that, we can also then get this k, which is the imaginary part of the complex refractive index. Here's our material that has light passing through it. The light is, once it comes out the other side, is our f lambda. Here's our kappa abs that goes in here, and here's the imaginary part of the complex refractive index. When we're actually doing this, what we will measure is the transmission, which is how much light makes it through the other side, and possibly the reflection and the thickness of our slab of material. And from those, the only unknown would be this kappa, which is the same as this kappa here. This is the absorption coefficient. And so we can then calculate this by measuring the transmission and the reflection. So measure transmission, measure reflection, we get kappa and therefore k, the imaginary part of the complex refractive index. We can also do this another way, which is to measure the transmission of the same material at two thicknesses. So the reflection both at the front side of the material and at the far side of the material is going to remain the same. It doesn't depend on how much the light is passed through. So we can just basically subtract these and get the difference between the thicknesses and the difference between the transmissions to get the kappa value and therefore the K. Once we've got K, we can calculate R. So remember, we've got this equation here. So we've got the transmission and the kappa. So now we can calculate R based on this two thickness model if we didn't measure it in the first place. And then either with the measured R or the calculated R, we can calculate M, because there's a relationship which we will derive later between the real and imaginary parts of the complex refractive index and the reflection. So this is how we actually can extract the information in the lab. So we're now going to get a relationship between the complex refractive index and the macroscopic optical properties of our material. So here I've got the incident light, A equals to A0 times a wave function, and the propagated light now has that complex refractive index in. So we've got the real part in here in the wave function that affects the speed, and we've got the imaginary part in here that affects the absorption. Now, across the boundary, that is, as it heads into here, there has to be a continuous magnetic and electric field. So we have tangential components must be continuous. So what that means is that we've got a certain amount of light on one side and a certain amount of light on the other. And so we're going to bring all of that together. So again, here we've got the incident light, reflected light, and the light that's propagated into the material. And a reminder here that we have the wave number is given by this zeta symbol, which is 2 pi over lambda, which is the same as omega over c. Our incident light is given by this equation, where this is the wave number. And our reflected light is basically the same, but moving in the opposite direction. So this symbol becomes positive instead of negative, but the speed is going to be the same. The transmitted light is now moving in the same direction as it was as the incident light, but it now has a different speed because it's moved into that new medium. Now, because we have to have continuity across the boundary, we have that the incident light plus the reflected light is equal to the transmitted light. At the same time, if we've got the incident light minus the reflected light, that is what is going in, but you've got to multiply it by the complex refractive index to account for that change in speed and absorption. So we've got these two equations that we can bring together. So here I've got, this is the incident light, the reflected light, the transmitted light, and the complex refractive index. So we bring them together. All I've done here is to put in AT here from over here, and then I've rearranged it a little bit. So I've got the reflection and the incident on different sides. And now I've rearranged it. So I've got the amplitude of reflected light over the amplitude of incident light in terms of the complex refractive index. Now remember, we already talked about this, that the amplitude is not the same as the intensity or flux. The flux is proportional to the amplitude squared, so we need to square this. But if we square this, then we've got the reflected flux over the incident flux, and that is the same as the reflectivity. So now we have a term for our reflectivity. So we've got how we can get the reflectivity from the complex refractive index. And now I've just put in the real and imaginary parts instead. So we have an equation that we can use to calculate if we can get K from measuring transmission, we can now get R by also measuring transmission and thickness, and then we can get out N from that value. So this is the equation that we just derived. Now I want you to think about what's going on here. If we have something that's very weakly absorbing, that means that the K value is very low. And so what that means is that this is an entirely real number. We basically have no absorption, and reflection is only dependent on the change in the speed of light. But as we've seen in previous videos, the real and imaginary parts are not completely independent. what we find is that as the K value goes up, that is the absorption gets higher, so does the N value, so does the change in the speed. And so what we find is that these two coincide. And so when K is high, N is high, and vice versa. And what we tend to get is an absorption and a reflection at similar wavelengths. So a wavelength or color at which something is strongly absorbing, it will also be reflective. What we can see here is we're going to get a strong absorption and reflection around 25-ish microns in this particular material. We've talked about how the dielectric function is derived from the polarizability of the material, but I want to talk about what actually contributes to the induced dipole moment that is the cause of this interaction of light and material. So we can think of it as being there are different dipole moments in a solid. They're going to be coming from three different components. We've got the dipole moment that is due to polar molecules in a solid. We've got the ionic polarization, and that's due to the relative movement of the ions in the solid. And then we have the electronic polarization, and that's where the electrons in the atoms are displaced relative to the nuclei of the atoms. So we've got these three different places that we can have affected by light, and therefore that contribute to the induced dipole moment. And they're going to contribute in different parts of the electromagnetic spectrum. So we're going to have these oscillators. We have a polar molecule, and it will have features that arise in the radio region. We'll have ionic polarization, and that's going to be in the infrared region. And then you're going to have the electronic polarization. So as the electrons are displaced from being evenly distributed around the nucleus, then we get a polarization there, and that will happen in the ultraviolet. We can expect solids to have features in their spectra in all of these regions. That is, that light can be absorbed in all of these regions, except for one. So we can have some ultraviolet absorptions or visible absorptions. We can have some absorptions due to polar molecules, but for the middle one, for the ionic polarization, that assumes that the solid is ionic. That is to say that there is an uneven sharing of the electrons between the two parts of the material. And so if you have something that is covalent, like say graphite, it is not going to give you any infrared features. You're not going to have that offset of the electric charge, and so you don't have that same effect there. So we do not always see infrared features. We will always see absorption, but not necessarily features that we can see that are due to this sort of induced dipole moment. Now, we've been talking about absorption and how as light passes into a solid, the electric field of the light interacts with the electrically charged particles. Now, if you remember Kirchhoff's laws, when we talked about this for just electronic spectroscopy, that you have emission and absorption are the opposite of each other. If you remember, you'll have an emission spectrum when your gas is hot, and you'll have an absorption spectrum when your gas is cool, and there's a light source behind it. At thermal equilibrium, that is to say, assuming that everything is in equilibrium with its surroundings from the point of view of energy flow, the emissivity is going to be equal to the absorptivity. So just like with the electrons jumping from level to level in a regular visible spectrum, the solid, if it has an absorption at a certain wavelength that's due to the spring constant and the damping of that spring, you will also have an emission at that wavelength when the solid gets hot enough. So if it absorbs a wavelength, it will also emit at that wavelength. How do we know whether we're going to get absorption or emission? Well, that again depends on temperature, just like it did with electrons in an atom. At low temperatures, the bonds in between the atoms are not vibrating very well. And so as the electric field hits them, you've got light coming through, the electric field hits them, and the atoms will be forced to vibrate. And they will vibrate most effectively where there is a resonance with the light. And so they will absorb those photons most effectively. But If it is at high temperature, now those bonds will vibrate anyway because there's a lot of energy stored in them, and they will vibrate most effectively where it is in resonance, that is, where it is the natural frequency for them to vibrate according to the Lorentz model for the solid. So what other effect might we expect temperature to have, apart from just whether you get an emission or an absorption? Well, here I'm going to show some data from this paper here. Think about a solid. When you heat it up, it's going to expand. And that's going to affect the separation of the atoms. So that affects the vibration. It will also affect the damping coefficient and the spring constant. So as you heat it up, you're going to have several different effects. In general, you would expect to see, as the temperature goes up, for the features to get broader and to be at slightly longer wavelengths because the separation has got bigger and you've got a bigger spread of options. So here, this is a figure from this paper by Koike et al. And it's plotting, this is the mass absorption coefficient, but remember that this kappa value here is directly proportional to the K value, and it's also what you would see in a transmission spectrum. So we can see here, this is wavelength in microns. We've got two different features. If we start with this red line here, we've got something that's peaking close to 50 microns. It's quite broad and not very strong. That's at 295 Kelvin. As we cool it down to 200 Kelvin, now it's at a slightly shorter wavelength and it's slightly narrower. We're going to cool it down another 50 Kelvin and it's got shorter wavelength and narrower. As we cool it down some more, it's getting more and more sharp, and it's going to be peaking at shorter and shorter wavelengths. You can see exactly the same trend in this feature, which is at around 69-ish microns, but you can see it moves from being around just under 70 microns to under 69 microns, depending on the temperature of the solid. This is from the same paper, so here you can see that 50 micron feature, and you can see that it's kind of broad and not very tall. It's getting narrower and taller, but you can also see that if we look at this feature here, you've got something that there's features there, but they're so broad that they're merging with each other, so they're not resolved as features. You just see kind of a shoulder on this bigger feature. But as the temperature goes down, not only do those features start to resolve, but they get sharper and sharper. You can see the same thing over here, where you've got a feature that it looks like a little weak feature, but as you cool it down, you start to see that there's actually two features involved. So the temperature can have a number of different effects, and what we see out in space is going to depend on the temperature of the materials. So what have we talked about in this video? We've gone through how the complex refractive index affects the propagation of light. We've talked about the wavelength regime that causes the polarization, that is the physical reason that light is absorbed. We talked about how only ionic bonds are going to give us infrared features. So for covalent bonds like carbon, you're not going to have any infrared big features of absorption. You're just going to have absorption across generally. We talked about what's going on when we've got absorption with cold solid material and emission with warm material. And then we talked about what other effect temperatures have.